In this set of notes, we're going to continue our discussion of multiple linear regression, and we're going to go back to when we looked at quantitative predictors. So far we started out by looking at quantitative predictors, then we looked at categorical, and when looking at quantitative, one of the things that we looked at was interactions. And so if you remember back to when we talked about interactions, we mentioned that interactions are a type of what we call second order term. When we have two quantitative predictor variables, if you look at the interaction, you've got those two quantitative variables multiplied by one another. Now there are other types of higher order models. And so the interaction term is just one type of second order term when you have two quantitative variables. There are other types of second order terms, and that's what we're going to start out looking at here. So again, all of the models discussed so far have been for straight line relationships between the expected value of y and the independent variables. So now we're going to discuss a model that allows for curvature in the relationship. So even when we looked at interactions before, even though they were a second order term, we could see that they could simplify to straight lines. But what if we have a curved relationship? So this is what we call a second order model, because it's going to include what we call an x squared term. So the quadratic model is a second order model that contains only one independent variable x, and you can see that model is given right here. So notice that in the model we have both x and we have x squared. And that x squared is what is going to allow for the curvature. Now if you remember when we talked about interactions, one of the things that we talked about was if the interaction term is included in the model, we also include the lower order terms. Well, the same thing is true when we look at the quadratic term. If the quadratic term is in the model, we're going to maintain the lower order term as well. So here's some examples of what we might see in our plot. We have what's called a concave upward. When this occurs, the coefficient on the x squared is going to be greater than 0, or we could have concave downward, and in that case the beta 2 is going to be less than 0. So here's kind of a summary of this second order model with a single quantitative independent variable. So we're still going to have that beta naught is the intercept of the curve. Beta 1 is what we call the shift parameter. So in other words, it shifts along the x-axis where the curve is located. And then beta 2 is the rate of curvature. Is that curvature really sharp? Is it just slight? And that's what beta 2 is going to control. So let's look at an example. So there's a website provided here which provides data on the number of HIV/AIDS deaths worldwide from 1990 to 2017. We're going to let x be equal to the number of years since 1990, and below is a scatter plot of the data. Now one thing to note here is this is technically time series data, and in practice I wouldn't analyze it this way, but we're going to look at this example for illustration. So if we look at this scatter plot, we can very quickly see that the points do not form a straight line, which is what we've looked at previously, and there is an obvious curvature here. So we'd like to build a regression line that can model that curvature. So here what I've done is I have fit that quadratic model that we just saw above, and this is the R output. And so our first question is, looking at the scatter plot, is there evidence to support the use of the quadratic model? And the answer here is obviously yes. Again, we can look at this scatter plot and we can see that there's an obvious curvature there in the data. So next, let's interpret those beta estimates. So we're going to start out with our intercept. So if we look up here, we can see the intercept estimate is given right here. And we can interpret it. So the interpretation says we expect that in the year 1990, now notice the reason this is for the year 1990 is the intercept looks at when x is equal to 0, and remember that x in this case is the number of years since 1990, so if x is equal to 0, that means we're in year 1990, to have 123,852.4 HIV, AIDS-related deaths. So the next question is the overall model useful for predicting HIV/AIDS deaths? We're going to test using the alpha 0.01 level. So as always, we're still making that assumptions based on the error terms. So the assumptions are the same as they were before. And again, for right now, we're not checking these. We're just going to assume that they are met. Next, looking at our hypotheses, we have two parameters in our model other than the intercept. So next thing we're going to do is we're going to go and look for our test statistic. So going up to our output, remember in R that the overall F test statistic is given here. So we see that our test statistic is 244.1. And again, in publications, it is common to give both those degrees of freedom. So notice here we have 2 and 25 degrees of freedom, and then our p-value is effectively 0. So in this case, we would reject the null, and we would conclude the following. So notice the overall conclusion for this model utility test is very similar to what we've seen before, and one of the important things to note is in the interpretation I am including what model we fit, because again, all of the values that we find are contingent on the model that was fit. Alright, next we're going to see if there's sufficient evidence of concave downward curvature in the number of deaths. So just as a reminder, if we go back up and we look at our pictures, notice this is concave downward. And visually this seems reasonable to test because based on the scatter plot, it appears there is downward curvature. So let's see if we actually have evidence of that. So again, the same assumptions apply. And notice again, if you've tested those in the test above, then we know that those assumptions would hold. Now here, since we are testing about the curvature, that is going to be the beta 2. And here's our hypothesis test. So next thing we need to do is go and look at our output. Notice since this is a test just for beta 2, we can use this portion of the output. So our test statistic in this case is negative 19.26. And our p-value is very small. So in this case, we are able to reject the null, and we can say the following. Alright, so we have at the 1% significance level, we can conclude that there is enough evidence of concave downward curvature with HIV/AIDS deaths as the response and years since 1990 as the predictor in the second order model. And so notice you do need this part because that second order model, that's what's telling you that you have years since 1990 and years since 1990 squared in the model. Alright, so this model that we just looked at, it's actually a special case of what is called polynomial regression. So a response that is a function of a single quantitative independent variable can be modeled by the first few terms of a polynomial algebraic function. So what do we mean by that? So let's have a look at our model here. So notice in our model we have the intercept, and then all of the corresponding terms only involve x, but they involve x to increasing powers. So we have x to the first, second, third, all the way up to the pth power. So notice if we just focus on this piece right here, that is that second order model that we just looked at. And it ends up that some of the models that we've already looked at are just special cases of this. That includes the simple linear regression model that we've looked at, as well as that second order quadratic model with one independent variables. Now, with any model that we fit, just kind of as a reminder here, we want to be careful that we don't extrapolate. So, for example, if we fit a second order model, a second order model might look like the blue line here. If our data is only in this piece right here, if we use that second order model to predict, let's say, here, notice we don't have any actual data. So our model would predict our response here, but it could be that the true relationship is up here. So again, just as a reminder, no matter what model we use, we want to be careful not to extrapolate because we can only look at that relationship or model what is happening within the range of the data that we actually observe. Alright, so how do you decide the order of the polynomial that you should use? So generally you want to start by constructing a scatter plot of the data points and see if you can determine a good approximating function. A pth order polynomial when graphed will exhibit p-1 peaks. So for example, a second order polynomial has one peak, a first order, which is a simple linear regression, has no peaks, third order will have two peaks, and so on. The third or higher order models are very rare, and I really do want to highlight that. Unless that, except for the case where response is a function of time, and then we model these actually in a different way. So I'm going to show you for the polynomial regression model, we can fit, fourth, fifth, sixth order terms, but in practice we rarely see anything higher than a second or third order, so keep that in mind. And actually that is a mistake. We are not, I'm just going to mark that out. I had pulled some of these from previous notes that I had. If you're interested in looking at time, we offer logistic regression, longitudinal courses, and in a longitudinal course you would look at what would happen over time. So here's an example of a third order model and what that pattern would look like. So notice here we have the interpretation of those parameters. Now one thing to be very careful about is once you get into polynomial regression, the interpretation of the parameters aren't as nice as they were in simple linear regression. Alright, so let's look at an example. So again, we're going to go back to that HIV and AIDS deaths, and so we saw this plot earlier. So let's see what would happen when we fit a third order model. And one thing that I want you to notice is if we look at the scatter plot, let's kind of look at the pattern. So initially we said, okay, yeah, there's definitely this type of pattern here. But notice if we look right here, it almost appears as if there could be a second curve. So keep that in mind. So here is our output. So let's look at this third order model and see if there's evidence that the cubic term contributes information for the prediction. Alright, so just like before, we would need to check our assumptions. And for right now, we are going to assume that those are met. And the cubic term is the third term. Now, one thing that I should note here is really before performing this test, I should do the overall model utility test. So we're going to assume that we did that and it was significant. And actually, if we go back and we look at our output, you can see that it is significant. All right, so testing for beta 3. First thing we need to do is we need to find our test statistic, which is going to be a t-test statistic. And notice that that information is given right here. So we have negative 2.96. And then for our p-value, we have 0.007. So again, notice that this is smaller than the 0.05, so we are going to reject. So in this case, we would conclude at the 5% significance level, there is enough evidence of a third-order relationship between number of years since 1990 and number of AIDS and HIV-related deaths. Now, so previously we fit a second-order model, and here we fit a third-order model. So let's actually look at this scatter plot down here, and let's look at that comparison. So here in the green, we have the third order model, and in the blue, we have the second order. And we can see that visually, there's not very much difference. If I had just plotted that blue and that green line for you, you would have thought, oh, well, these both just look like second orders. The reason what's happening here is for that third order model, the way that it's fit is that second curvature is actually off of the chart here. So that's why we don't see that. So notice the two models are actually very close to one another in terms of fitting the scatter plot. And so you might ask in practice, which one would we use? Well, in practice, when you're choosing models, we're going to talk more about model selection later on, you generally want to choose something that is simple as possible, but still does a good job at explaining what is happening. So let's go through and actually go back up in our output. One way to make this comparison is to look at the value of r squared. So notice here for our third order model, we have an r squared of 0.9643. If we go all the way back up here to the output from our second order model, notice here, oops, we have an r squared of 0.9513. So notice we're gaining very little by moving to the third order model. So even though the third order model is significant, since I'm not gaining that much in r squared, in practice I would probably just stick with the second order model. And so this is one of those things that can get really tricky when we start talking about models, and we can't just rely on what the hypothesis test tells us. We also have to make decisions as the person, that's analyzing the data and looking at what's happened. And it actually ends up in this case, you could even fit a fourth order model, and the fourth order model is still going to be significant. But if you looked at the plot of the comparison, you would see that the model looks very similar to the third and the second order, and you won't gain very much in r squared. So again, you want to keep all of this in mind. It's this holistic picture of which model we actually end up choosing. So in this case, I would just go with the second order model. All right. So now we're going to continue looking at second order models, but we're going to look at models with two or more quantitative independent variables. So far we've just looked at second order models that have a single quantitative variable. So second order models with two or more independent variables permit curvature in the response surface. The interaction model is a twisted plane in the three-dimensional space, so that's what you're seeing here. And the second order term, beta 3, x1, x2, is called the interaction term, and it permits contour lines to be non-parallel. And so we've actually seen some of this before. Alright, so here's the second order model with two independent variables, and again, we've seen this model before, so this one is not new. Alright, so the addition of a quadratic term, though, allows for more flexibility in the model, and this is now what we call the complete second order model. And so this model is going to be new. It's going to combine the models we've previously looked at. So two variables x1 and x2 are said to interact. Again, if the change in probably expected value of y for 1 unit change in x1 when x2 is held fixed is dependent on that value of x2. So here we have what we call a complete second order model with two independent variables. And the reason that we call it the complete model is, notice it is going to have all of the possible second order terms. So it has that interaction term, which is a second order term, and it also has the quadratic term for both x1 and x2. So this is why we call this a complete second order model. And here's some pictures of what these surfaces could potentially look like. And I'm just going to write this down here at the bottom. This is what ends up, you have the relationship of the parameters that create surfaces like this. You don't have to memorize this. This is just more for your information and how the values of these parameters are relating to the different potential surfaces that you could see. So one way to think of this is when we're looking at simple linear regression, we know that if beta 1 is greater than 0, we expect the plot to go up and to the right. If it's less than 0, we expect it to go down and to the left, and so we can tell that just on the sign on beta 1. Well, when we look at these surfaces, it's more complicated, so we actually have to look at the relationship between the different parameters, and so this is how you would get these different surfaces. All right, let's look at an example. A study of street vendors in the city of Pueblo, Mexico examined the mean and annual earnings as a function of age and hours worked. We're going to start out by writing a complete second order model for the mean annual earnings as a function of age and hours worked. So here we're going to treat age as x1 and hours worked as x2. So here is our complete second order model. And one thing that I should note here, the order of the terms doesn't actually matter. So for example, I could have had beta 3 be the coefficient that goes along with x1 squared and rearrange these. The only thing that's going to change is the interpretation of those parameters later on. So we're going to look at some output and we're going to find the least squares prediction equation. So let's go ahead and look at that output down below. So the output is right here. So notice here we have all of our parameter estimates, and these parameter estimates are what helps us write out the prediction equation. So let's go ahead and write that out. Now one thing that I do want you to note here is be careful, because notice that the way that SAS has output these is in a different order than what we wrote up above. So notice here we've got the interaction term, here we've got age squared, and here we have hours squared. So we want to make sure we're careful when we translate those values back into our model. All right, so looking here at our model, the first thing I'm going to do is just write out the generic form of the prediction equation. So there's our generic form. So now what we could do is we could go through, look at our output, and fill each of these values in, and we get the following. Okay, so the next question is the model statistically useful for predicting annual earnings? So again, this is that model utility test that we've looked at several times. So here, and again, you would always start out with your assumptions. Notice here we have 5 parameters. And then to get your test statistic and your p-value, you would go to your output here, and here is our test statistic and our p-value. Notice here our p-value is less than 0.05, so we would reject the null hypothesis. So I'm going to leave you to finish this one on your own, because again, that's very similar to what we've done before in terms of our writing our test statistic and our p-value and our conclusion. Alright, so next, how would you test the hypothesis that the second order terms in the model are not necessary for predicting annual earnings? So, if we wanted to test this, notice that our second order terms are the terms dealing with x1, x2, that interaction, the x1 squared, the x2 squared. And so really what we've got here is there are 3 parameters that we are interested in. It's the beta 3, the beta 4, and the beta 5. So to set up this hypothesis test, we would want the following. So to test this, since we're testing to see if some of the parameters are equal to 0, and we've got more than one of them, so we can't use those t-tests, this is where we would use that nested f-test that we saw earlier. Because notice here, what we've got is our full model. Well, that's the model that we have right here in part A. The reduced model that's going to be the model that just has the following. So we can use that nested f-test from the previous note set to test whether or not we need those second order terms. So let's go down and look at our output here. So just as a reminder, some of the things that we need are going to be the SSE and the MSE for the full model. And then notice if you go down to the next page, I've actually already given you the output for the reduced model. So here you have the SSE for the reduced model. Now the other thing that I've included in this note set is we can actually have SAS conduct this test for us, and that's in output 3. And so you'll see that output is given right here. So notice if we look at our output, here is our f-test, and for this case we actually fail to reject the null hypothesis, so we are not able to prove that we actually need those second order terms. So I'm going to leave this for you to try on your own, and I would suggest trying this 2 ways. 1, go back to the previous note set, see if you can find the test statistic for this nested f-test. And the way to see if you got it correct or not is to go to output 3 here on page 15, and again this should be the f-value and the p-value that you find. And remember, to get the p-value you'll have to use r. And then again you could write out the conclusion here. We fail to reject the null at that 5% significance level, and we don't have enough evidence to show that we need those second order terms in the model. So in this case we would actually just revert back to the model that has the 2 first order terms in it.